Thus far, the only operator we've considered has been the energy operator, that is, the Hamiltonian. As we mentioned, for every measurable physical quantity in quantum mechanics, there should be an operator. As we prepare here to look at the uncertainty principle, a relation that applies to the measurement of position and momentum, we will first formally define the operators associated with these measurable quantities. Of course, these will allow us to define and calculate expectation values of both position and momentum. We will start first by formally introducing the momentum operator.
So, for momentum, we're going to write an operator. So we put a little hat over this P, and we're simply going to postulate that this momentum operator can be written as minus I times h bar times the gradient operator. And of course, the gradient operator is just this set of derivatives in each of the coordinate directions. And here, to avoid some other confusions, we're defining x0 and y0 and z0 as unit vectors in the x and y and z directions. So therefore, we're saying the momentum operator is minus I h bar times the gradient, the spatial derivative operator in vector form. So with this postulated form here that our momentum operator is minus I h bar times the gradient operator, we find that if we simply square this operator and put it over 2m, then what we have is minus h bar squared over 2m times del squared. And of course, we recognize that from being part of Schrödinger's equation. And we see, therefore, that with this choice, which we have just postulated, we're beginning to see a correspondence between the classical notion of the energy, E, which is p squared over 2m in classical mechanics plus v, the potential, and the corresponding Hamiltonian operator of the Schrödinger equation. So the Hamiltonian operator with the hat being minus h bar squared over 2m del squared plus v. And we could rewrite that with our new definition of the momentum operator as the momentum operator squared over 2m plus v. Now, note that if we operate on the state e to the I k dot r with the momentum operator, that would be minus I h bar times the gradient of e to the I k dot r. If we take the gradient of e to the I k dot r, using the components in each of the different vector directions and all of those different vector components of the gradient, we're going to get I times k e to the I k dot r. And that I times the minus I we had here just gives us 1. So the effect of minus I h bar times the gradient on e to the I k dot r is to give us h bar k times e to the I k dot r. Now, so far, this is just a mathematical operation saying that if we operate with the momentum operator on this kind of plane wave spatial state, we're going to get h bar k times the same plane wave spatial state. Well, that means that these spatial plane waves are actually the eigenfunctions of the operator P. And they have eigenvalues h bar k. Why do we say that these plane waves are the eigenfunctions of this operator P with eigenvalues h bar k? This is a vector eigenvalue, but that's a detail. Well, the reason is that we operated with this operator P on this function and found that we got this value, in this case a vector value, times the same function. That means, by definition, that these functions are the eigenfunctions. And these h bar k's here are the eigenvalues. Now, as I said, these are vectors in this case, but it's still the same basic idea. We can therefore say for these eigenstates that the momentum is h bar k. That's the eigenvalue of the momentum in this state. It's a perfectly well-defined value, a vector value, when we have this kind of state and we operate with P. Note that P here is a vector, with three components with different scalar values. And it's not an operator. This P is not an operator. It's just a vector, which we can say is momentum if we happen to be in this particular kind of state, e to the I k dot r.
Now, up to this point, we've only been talking about eigenfunctions and eigenvalues of energy. Here we are saying that we have a new operator, one representing another physical quantity, here momentum. And this operator also can have eigenfunctions and eigenvalues. It's important to understand that these are not necessarily also eigenfunctions of the energy operator, that is, of the Hamiltonian. For the particular case where the potential is constant everywhere, the momentum operator and the Hamiltonian happen to have the same eigenfunctions. But generally, they do not. If we add a potential into the Hamiltonian, we will get some different set of eigenfunctions for the Hamiltonian. But the eigenfunctions of the momentum operator remain unchanged. They are still these plane waves. At the very least, we're making a mathematical statement. For the operators that we come across that represent some physical quantity, such as energy, or momentum, position, or angular momentum, each one of these will have its own eigenfunctions and eigenvalues. The energy eigenfunctions have the special property that they represent states that are stable or constant, or what we might call stationary in time, as far as any measurable quantity is concerned. In general, the eigenfunctions of other operators, like momentum, do not represent states that are stable in time, unless they also happen to be eigenfunctions of the energy operator. Mathematically, the existence of these eigenstates and eigenvalues of these other operators is quite important as we handle quantum mechanics. But, as I said, they don't necessarily have the particular properties of the energy eigenstates of representing systems that are stable or stationary in time. To emphasize, for the momentum operator, we just made the observation that if we operated with it on a plane wave state, e to the I k dot r, then we got a constant, here h bar times the vector k, times the function. By the definition of eigenfunctions and eigenvalues, that means, as we have pointed out, that this plane wave is necessarily an eigenstate of this operator. In this case, with the vector eigenvalue h bar times the vector k. Since such spatial plane wave states generally can be used to describe any function in space, a fact we may already be familiar with from Fourier transforms, we're seeing that this set of eigenfunctions is also a complete set. Again, we will see this property of completeness rather generally for the eigenfunctions of quantum mechanical operators representing physical quantities. Now let's look briefly at the position operator.
For the position and the position operator, we simply postulate that the operator, which turns out to be almost trivial when we're working with functions of position, is simply the position vector r itself. At least when we're working in a representation that is in terms of position, we therefore typically do not write r with the little hat on it, though perhaps rigorously we really should do that. The operator for the z component of position would, for example, also simply be z itself. As I said, this is a consequence of the fact that we're working in what we call the position representation. We're still talking about functions that are functions of position. We're essentially writing down a list of values of the function for each different position as the way we're thinking about the function. And because of that reason, we tend to think about the position operator as just being the position itself.
Now we're going to take our first look at the uncertainty principle. A commonly quoted form is to say that we cannot simultaneously know both the position and the momentum of a particle. Another form would say that measuring a system necessarily changes it. Actually, stating the uncertainty principle these ways, especially that second one about changing the system, is really mixing up two different things. One aspect is quantum mechanical measurement. There we say that measuring a quantity collapses it into an eigenstate. Now, as we've discussed, this has at least philosophical problems, and arguably we don't really understand this process. We could say that this issue is not the uncertainty principle, however. This is the measurement problem. A second and quite separate issue is the notion that it's not meaningful to require the state of a system to simultaneously have well-defined values of two specific quantities. This is what we will be referring to as an uncertainty principle, and at least in our minds, we're separating it out from the measurement problem. At the time when the uncertainty principle was first being discussed, understandably these two issues were mixed together, and in popular discussions that mixing continues to this day. In our discussions, though, here we're going to separate these two problems. The second problem of a physical state not being able simultaneously to have well-defined values of two specific physical quantities is not actually a problem in quantum mechanics, and is something that occurs in many situations in the classical world without causing any real confusion. We already mentioned this point briefly. A good example is that a musical note or tone must be long enough if it's to have a relatively well-defined frequency. We can notice if two musical instruments are slightly out of tune if they play for a long enough time. If the note is long, however, it does not have a well-defined time associated with it. A short musical note does not have a well-defined frequency, but it does have a relatively well-defined time. This phenomenon of the inverse relation between time and frequency uncertainties is well known in Fourier analysis. Now, we will have a first look at this uncertainty principle for position and momentum. The only real surprise here is that, before we started on our quantum mechanical view here, we just did not expect this phenomenon for particles with mass. Now that we are describing them as waves, however, this uncertainty principle arises naturally, just as it does for other wave or oscillation phenomena.
Now we're going to have our first look at the uncertainty principle then. And here we're going to illustrate the position-momentum uncertainty principle by an example. Actually, we're going to take the example of a Gaussian wave packet. We've looked at Gaussian wave packets before, and we know that we could write those as a sum over waves of different k values with Gaussian weights, with Gaussian amplitudes in front of each of those waves with different k values. And perhaps slightly more elegantly, we could take the limit of that sum by using an integration. It's really still the same thing as a sum, just it's mathematically slightly more elegant to write it this way. So our Gaussian wave packet then is a sum over several different waves, in fact, every wave with different k in a particular range, with these Gaussian factors weighting them out the front. So this is just a Gaussian wave packet. Now we could rewrite this Gaussian wave packet here at specifically the time t equals 0, just as this simpler expression here. In other words, if we put t equals 0 in here, then the expression simplifies down, where this psi with a subscript k of k is just this expression here. It's just our Gaussian weights, our Gaussian amplitudes for each of these different waves, in this case at time t equals 0. So in this expression here with these Gaussian weights, we could say that psi with the subscript k as a function of k is the representation of this wave function in k space. This is the set of amplitudes in k space of all of these plane waves. So this is just as good a representation of the wave function as the set of all of the amplitudes in real space. And with that statement that these are the amplitudes in k space, then we can interpret the modulus squared of these amplitudes as being the probability p sub k, strictly the probability density in k space now, that if we measured the momentum of the particle, actually the z component of the momentum, because we're only working in one direction here at the moment, it would be found to have the value h bar k. So we're interpreting this as a probability or probability density that the particle would be found to have momentum in the z direction of value h bar k. Now, with this expression here, these set of amplitudes, then this probability density of finding a value h bar k for the momentum when we do some measurement would be, as we said, this modulus squared of this amplitude here, and that would be proportional to this exponential here. Note a slight difference. The 2 was inside the squared here. The 2 is now outside the squared here because in taking the square here, we've multiplied by 2 on the top line. So that's cancelled one of these 2's down here, leaving just one of them. And this Gaussian corresponds to the way that a statistician would write down a Gaussian probability distribution, with this parameter, delta k, being what a statistician would call the standard deviation. So this expression here is a set of probabilities that happens to be written in such a way that they look like the Gaussian distribution in statistics, with this standard deviation, which is a standard statistical term to express the width of a statistical distribution. Note also that the wave function expressed in space here is written down like this at time t equals 0. We saw that before. That is technically what is known as the Fourier transform of this function. And it's well known from the mathematics of Fourier transforms that the Fourier transform of a Gaussian is also a Gaussian. And that makes the Gaussian a very convenient function to work with here in our example. Specifically here then, the Fourier transform of this Gaussian function here, which is formally this expression, is this Gaussian now in real space, now as a function of z here. And it's not quite written yet in the form of what we would regard as our statistical form we're going to get to for the modulus squared here. So if we do rewrite this modulus squared of this function now of position, our Gaussian in position, of course the modulus squared would look like this with a 2 in here. If we want to put that into a standard form for a Gaussian, for a probability distribution that would be in a standard statistical form, which would be in this form with some width parameter in real space, delta z down here, and our factor of 2, then we would now be looking at the standard deviation. This delta z would be the standard deviation for the probability distribution for measuring position z in real space. Now, to make these two expressions be the same thing, of course, so in other words, to find what this delta z is in terms of the delta k, well, that's algebraically quite simple, just comparing these two expressions. What we would find is that for this to be the standard deviation in space, when this is a standard deviation in momentum space, the product of delta k times delta z is equal to 1/2. In other words, these two expressions are the same thing if delta k and delta z multiplied together give us 1/2. You can check that out by comparing these two expressions. Substitute this in, we can get from one expression to the other. From this expression here, then we can multiply by h bar, and that would get us, for h bar k, the standard deviation we would measure in momentum. We could call that standard deviation in momentum, h bar times delta k. We could call that delta p. And then this expression, delta k, delta z equal to 1/2, turns into this one. Delta p times delta z equal to h bar over 2. And what this is for our Gaussian wave packet, this is the relation between the standard deviations that we would see in measurements of position, so the statistical variability of our measurement of position, and our measurements of momentum. We measure position, we get some variation in the answers we get statistically. We measure momentum, we get some variation in the answers we get statistically. We can describe those variations in terms of the standard deviations, delta p and delta z, of those statistical distributions, and what this expression is telling us is that the product of these two standard deviations in this case is equal to a specific quantity, here h bar over 2. This relation that we have here is as good as we can get for a Gaussian. For example, if we have that Gaussian pulse and we let it broaden in space as it propagates, it's still got the same range of k values in it, but it's become broader in space. So that was the best that we could do there, was that relation. And it also turns out that this Gaussian shape is the one with the minimum possible product of these standard deviations. We're not going to prove that here, but we will come back later on to prove this mathematical minimum, and the Gaussian happens to be as good as you can do. So quite generally, therefore, we can write that delta p times delta z is greater than or equal to h bar over 2. And the greater than or equal to is for two reasons. The first is that if we let our Gaussian propagate, it will get a little bit wider anyway, so the delta z will increase even if the delta p did not. So we'd have to have a greater than or equal to from our Gaussian experiment, as it were. But as we said, the Gaussian is also the best possible shape. Other shapes give us worse products of delta p and delta z, so they would also be greater than h bar over 2. And this, of course, is our uncertainty principle for position and momentum in one direction.
What this uncertainty principle implies is that if we make our Gaussian distribution here narrower in space, it gets broader when we look at the distribution of momenta used to make up the pulse. And if we make our Gaussian distribution broader in space, it gets narrower when we look at the distribution of momenta. It's this inverse relationship between width in ordinary real space and width in what we call momentum space that the uncertainty principle is describing for us. Though demonstrated here only for a specific example, this uncertainty principle is quite general. It expresses this non-classical notion that if we know the position of a particle very accurately, we cannot know its momentum very accurately. Our modern understanding of quantum mechanics says that it's not merely that we cannot simultaneously measure these two quantities, or that quantum mechanics is only some incomplete statistical theory that does not tell us both momentum and position simultaneously, even though somehow they both exist to arbitrary accuracy. Quantum mechanics is apparently a complete theory, not merely a statistical image of some underlying deterministic theory. A particle simply does not simultaneously have both a well-defined position and a well-defined momentum. As we said, this notion is quite common also in the classical world. We mentioned it in the relation between uncertainty in time and uncertainty in frequency. We can look at that one more explicitly.
Of course, this kind of uncertainty principle is already well known in the mathematical subject of Fourier analysis. One cannot simultaneously have both a well-defined frequency and a well-defined time for a signal. If a signal is a short pulse, it is necessarily made up out of a range of frequencies, some range of order delta omega, for example. And in that case, we would, by similar mathematics, in fact ultimately identical mathematics, we'd be able to prove that the product of these two width parameters, the width in frequency and the width in time, when we're talking about angular frequency here, would be greater than or equal to a half. That's simply a mathematical statement that will fall out if we do the analysis, the Fourier analysis, of signals. The shorter the pulse is, the larger the range of frequencies. As I say, this is a normal phenomenon in signals in time and frequency.
Another good example is diffraction, which we looked at previously for waves in general. There we saw that if the aperture was small, the beam had a wide divergence angle. And if the aperture was large, the beam had a narrow divergence angle. This is an exactly similar uncertainty principle. Indeed, it's also possible to interpret the width of the pattern in the far field over here as representing an uncertainty in the momentum of the particle in that vertical direction, and the width of the aperture as the uncertainty in the position in the vertical direction, in which case we get back exactly the same uncertainty principle for position and momentum that we've been discussing.